Friends, myself, Professor Joshi VM from ADSUL'S Technical Campus, Charles, Ahmednagar. Today we discuss further concept of transformer. Last lecture we have discussed about what is the meaning of transformer, what is its working principle, what are its types. After that, we briefly explain the types of transformer like shell type, core type, and vary type of transformer. We discuss about the various parts of transformer, their functions, their materials, etc. So, today's lecture we have to discuss what is the meaning of transformation ratio, what is the EMF of transformer, what is the EMF of what amount of EMF is induced by the primary as well as the secondary winding of the transformer. After that, we have to discuss what is the meaning of voltage and current ratio of the transformer. After that, what is the EMF equation of transformer, what is the transformation ratio of transformer. After that, types of transformer on the basis of their transformation ratio, or that is the value of K. After that, rating of transformer. After that, losses of transformer, what are the types of losses of transformer, and finally we have to discuss about the how to reduce the losses of transformer. So let's start our session from EMF equation of the transformer. There are two types of EMF equation of transformer. First is E1, that is EMF induced by the primary winding, and second is E2, that is EMF induced by the secondary winding. So we will draw here a circuit diagram. By this circuit diagram, we will briefly explain what is the EMF ratio of transformer. So this is the core of a transformer. It is called core, which provides magnetic path for the magnetic flux travel from the primary winding to the secondary winding. This is the primary winding of a transformer. This is so we call it as the primary side of a transformer. This is the secondary winding of a transformer. So we call it as a secondary winding of a transformer. These are the number of turns of the primary winding. So we will give a name as N1 and we will give name as N2 for number of turns of a secondary winding. Okay. After that, the current which passing through the primary winding is called as I1. After that, the current which passes through the load or passes from the load is called as secondary winding, which is mentioned by I2. Secondary current flow towards the load. Sorry, secondary current flow from the load side is I2. Okay, and here supply is V1 and terminal voltage across the load is V2. The EMF induced by the primary winding is E1. EMF induced by the secondary winding is E2. These are the basic names of the various points, and the full form of this nomenclature. E1 is EMF induced by the primary winding, E2 is the EMF induced by the secondary winding, V1 is the supply voltage of primary side, V2 is the voltage across the secondary side. After that, I1 is the current of primary side, I2 is the current of secondary side. Here phi is the flux that flow from primary winding to the secondary winding. These are the same short form of the various norms. Okay, then what is the EMF ratio? The EMF ratio is the EMF induced by the primary side as per the Faraday's law is denoted by E1. The formula for the induced EMF E1 is 4.445 F M1. Here 4.44 is a constant form factor term. After that, phi m is the maximum flux produced by the winding, F is the supply frequency, and here M1 is the number of turns of secondary winding. So on another side of the winding, that is N2. So the induced EMF for secondary winding only changes in the number of turns of secondary winding. So here we draw 4.44 F 5 M F, and instead of N1 we have to write here N2. This is the number of turns of secondary winding. This is the EMF equation of primary as well as secondary winding. Okay. After that we have to take definition of transformation ratio. First of all, the transformation ratio is denoted by capital K. Is denoted by capital K. And what is the definition of transformation ratio? Transformation ratio is defined as it is the ratio of secondary voltage to the primary voltage, or it is the ratio of number of turns of secondary winding to the number of turns of primary winding, or it is the ratio of secondary induced EMF to the primary induced EMF. So what is the formula for K? K equals to V2 upon V1 equals to N2 upon N1 equals to E2 upon E1. Okay, this is the formula for transformation ratio, that is denoted by the K. Means it is the ratio of secondary voltage to the primary voltage, or it is the ratio of secondary number of turns to the primary number of turns, or it is the ratio of secondary induced EMF to the primary induced EMF. So there are some types of transformer depending upon the ratio of transformation ratio, that is K. Means there are some types of transformer depending upon the value of K. So if the value of K is greater than 1, okay, firstly if the value of K is greater than 1, then the transformer is called as step-up transformer. Okay, then the transformer is called as step-up transformer. After that, second, if the value of K is less than 1, that means K is less than 1, then the transformer is called as step-down transformer. Then the transformer is called as step-down transformer. And third type is if the value of K is equals to the 1, then the transformer is called as 1:1 transformer. 1:1 transformer, or 1:1 transformer, or ideal transformer if the value of K is equals to the 1. These are some types of transformer depending upon the value of K. After that, third is what is the definition of voltage and current ratio. Then what is the definition of voltage ratio? Then the voltage ratio is defined as primary voltage. It is the ratio of primary voltage to the secondary voltage. That means voltage ratio equals to V1 upon V2, because it is the ratio of primary voltage to the secondary voltage, and the equation becomes voltage ratio V equals to V1 upon V2. After that, current ratio. Then what is the definition of current ratio? It is somewhat reversal definition of voltage ratio. That means it is the ratio of primary current to the secondary current. That means current ratio, I ratio is denoted by, or it is defined as, it is the ratio of primary current to the secondary current. Means I ratio equals to, or current ratio equals to I1 upon I2. Okay. After that, third definition is turns ratio. Turns ratio. Turns ratio. The turns ratio is defined as number of turns of secondary winding to the number of turns of primary winding. So, number of turns of secondary winding is denoted by N2. Number of turns of primary winding is denoted by N1. So, this is the ratio of number of turns of secondary winding to the number of turns of primary winding. So, it is a very simple definition of turns ratio, voltage ratio, and current ratio. Voltage ratio is V2 upon V1, current ratio is I1 upon I2, and the turns ratio is N2 upon N1. So, after that, rating of transformer. We know that every electrical machine, the rating of every electrical machine is depend upon the how much amount of output power is delivered by this machine. It depends upon the output power. But in case of transformer, the output power is not a constant power. It is continuously variable power, because the output of transformer is not constant. It continuously changes. Which load we connected to the transformer, that shows its output power. So the output power of transformer is not a constant, and if the output power or the output of a transformer is not a constant, then the power factor is also not a constant. Means output power is totally depend upon voltage and the load current that is connected to the secondary side of the transformer. So transformer rating, because of that, transformer rating is always measured in voltage and current. So transformer rating is equals to, is also called VA rating. Is also called VA rating, which stands for voltage into A stands for current. Means voltage into current rating is VA rating. Next, losses of transformer. We know that the efficiency, what is meant by the efficiency of transformer? The efficiency is nothing but the eta equals to output power upon input power. Efficiency is nothing but the output power upon input power, and the output, if the output is 100 and the input is 100, then the efficiency is also 100%. But the output of every system or every machine is an addition of actual output plus losses. This is the actual output plus losses. If we reduce these losses, the output power is increased. Okay, output power is increased. So to increase the output power, we have to reduce the losses. That means losses reduces the performance of the machine or the performance of the transformer. So there are two types of losses in the transformer, losses are two types. First is copper loss, we call it as PCU, and the second is the iron loss, we call it as PI loss. Okay, there are two types of losses in transformer. First is PCU, that is copper loss, and another is PI, that is iron loss. This iron loss also be divided into two types. First is hysteresis loss. Hysteresis loss, and second is AD current loss. Second is AD current loss. These PI losses get divided into two types: hysteresis loss and AD current loss. After that, this PCU is a nothing. This copper loss is totally depend upon the winding of the transformer. It is totally depend upon the winding of the transformer. If the winding of transformer provides a resistance, then this loss gets increased. But we reduce the if we reduce the resistance of copper loss, then the losses, the total losses also gets reduced. Then how to denote this copper loss? The copper loss PCU equals to, there are two types of winding in the transformer. That's why there are also two types of losses present in the winding. For primary side, it is I1 square R1, means this copper loss is the square of load current to the resistance of the winding. So if we have to reduce the iron loss, we have to reduce this R. So for secondary side is I2 square R2. That means total losses PCU equals to I1 square R1 plus I2 square R2. If we have to reduce the copper losses, we have to reduce the R1 and R2, and the square of current primary as well as second totally depend upon the load. If we increase the load, then this square current is again also increase. If we decrease the load, then this square of phi is also reduced. That means the load is variable. Because of that, the copper loss PCU is also variable loss. It is not a constant loss. Then second, iron loss. It is denoted by PI. This iron loss is totally depend upon the magnetic iron core of the transformer. This totally depend upon the magnetic iron core of the transformer. So this iron, we cannot change the iron core of a transformer every time. So this kind of, and after explaining briefly this iron loss, we found that this loss also depend upon the supply voltage and frequency. So we cannot change the iron core of transformer, we cannot change the frequency, we cannot change the voltage. Because of that, the iron losses or PI losses are called as constant losses. Okay, this iron core losses are also divided into two types. First is hysteresis loss and second is AD current loss. Okay, first is hysteresis loss and second is AD current loss, or PHPE plus P. First of all, we discuss about the hysteresis loss. What is meant by hysteresis loss? This hysteresis loss is totally depend upon the supply frequency and voltage. Okay, supply frequency and voltage. So the pH, the formula for the pH is, KH Bm raised to 1.67 into FV. Kh is the hysteresis constant, Vm is the magnetic flux density. After that, F is the supply frequency and V is the supply voltage. Means we cannot change any term, so Ph losses are constant. Ph losses are constant. After that, next is eddy current loss, PE losses. For formula for the PE losses is KE Vn square F square T square. Means K is the hysteresis constant, eddy current constant. Vm is the square of magnetic flux density, F is the supply frequency, and T is the thickness of the lamination, square of thickness of the lamination. So then question arises that how to reduce this type of losses. Okay, so if we have to reduce the iron core losses, we have to take iron core like a silicon steel material, cast iron material, and to reduce the eddy current losses, we have to take number of laminations of the magnetic core. If we take number of laminations of the core, we can reduce the eddy current losses. If we choose a material like iron core or cast iron, then we can reduce the hysteresis losses. So today's lecture we discuss about EMF equation, transformation ratio, voltage, current, and turns ratio. Then types of transformer on the basis of value of K. After that, rating of transformer, and briefly explain the losses of transformer. Okay, thank you.